Okay, so how did we structure the talk? We have 3 parts. Yeah, it was too fast. So first of all, I want to give you a start why it's important what we're doing. And it's not only important, but it's actually a totally new area of computing that we are currently entering. And I want to briefly motivate it and also show you a little bit about the history of computing, because this is something that everybody should know, and it's also leading us to our topic today. Then we look at IoT meets AI from the industry perspective. Chris will take over and will present us challenges and opportunities that are currently very important for industry, for Siemens in particular. And then I will give you some intro to research, what is the research, what is my team at the moment doing, which are challenges that we are currently tackling. Okay, good. Starting with the first part. Are we in the matrix? Okay, so you probably have seen the movie. So who has not seen the movie? Okay, so 1. Who has seen the movie? Okay, you all have hands, very good. Okay, so yeah, so this is a screenshot from the movie. Normally I show a little video sequence, but I was not sure with the copyright if this is okay, therefore I just put the pictures. So these are these 3 agents, and when you think about the scene, this is one of the key scenes. Then soon after, he sees this, which is like the matrix, even though he's currently in it. And what do we see here? Well, we see that we have something that symbolizes here the code that is running, and the code is creating our reality. And are we in the matrix? So, well, I would say we are somehow in the matrix today, because with the IoT, we are able to control our environments. So this is now a private space, for instance, or an office space like this one here, and we have sensors and actuators distributed, and these sensors and actuators are connected to a brain, which in the case of computer science is then a processor, and then we can control our ambience by the programs. And a MIT program, or something that is currently more vogue, is using machine learning. This is also something that we'll do in the upcoming days. And what I like to tell people when I say, okay, what is my research, what am I doing there? Well, I'm kind of doing magic, because how is doing magic? Magic is you say a spell and then something happens and something changes. And doing smart space orchestration, so by using software to control the environment, is something very similar, because it's like when you have your smartphone here and you start the app and then your environment is suddenly starting to transform. Or you don't even need that, you just enter the space, the lights go on, and something like this is happening. And this is like magic. It's like putting a spell on the environment. And the spell is your programming language, and you can program the things that you want to orchestrate. This is what we'll do in the upcoming days. And I really like this analogy, because I always wanted to be a wizard, and so somehow we can be a wizard. This one is also a very good example, the smartphone, because it's a small IoT space. It has also sensors and actuators, and they are inside this shell here, and you can use software to control them. So these are the key issues here. Okay. So, yeah, we're somehow in the matrix. We can not only control the private spaces, but also public spaces, industrial spaces. This is what we look at in the next days. When we look at a time frame here, so probably before many of us were born, we had the area where we had mainframes. So this was people going to the cellar and using the computers there. Then afterwards, in the 1980s, 1981, we had the personal computers. Huge change. So it was not something happening in the cellar, but it was you could take it home. You all grew up with personal computers. Then it continued. The next wave that we have was mobile computing, with the Apple devices as iconic devices, because they managed to, for the first time, to really implement this software for controlling the hardware, creating a software ecosystem for controlling the smartphones, for managing them. This was also a milestone because it was having multi-users using the same device. And what is happening today is that we have pervasive computing, and while mobile computing here means computing everywhere, so we have our smartphone with internet connectivity, we can use the backbone everywhere. Pervasive computing means that we have computing in everything. So we can remotely manage all the entities that we have in our spaces. These public displays are good examples for it, for applications that we might have in the near future, that you are in the train station and the display is reacting to you. For advertisement, you partly have it already. And the last two together, they are called Lubricators Computing. What is interesting here is the interaction scheme. So at the beginning, you had multiple people using one computer, personal computer, you had one person using one computer. Then we shifted towards one person using multiple devices. So I'm quite sure that all of you have at least 2 compute devices with you. And when the pervasive computing will be reality, or how it is already when you're in factories today, for instance, or in buildings that are smart, is that you have many people that are using many devices, and so the relationship is not anymore this is your device, but it's you, and you're entering a space, and there are devices, and you're interacting with them. Okay, good. So these are 3 phases, and the third one is the thing that is currently getting reality. And now let's have a closer look at how this path went. And so these are 5 pictures. So these are 5 videos that I want to share with you. And I want you to guess when the video was taken. The quality of the videos is just like that because I took them from the internet. So you cannot necessarily guess from the quality of the video when it was taken.
I'd like to see you while I'm working on it. So before I can do that, I have to set up my display in a certain way. So I see it over like that. It leaves a corner up there, and I say, now computer, do the automatic switching that is bringing in a camera picture from the camera mounted on his console, which is the camera mounted on mine. There you go. That's great. Now we're connected audio, you can see my work, you can point at it, I can see your face, we can talk. So let's keep and collaborate.
Okay, so we have seen there's some kind of video chat and some interaction between the 2 people there. Yeah, when do you guess was this recorded? 83. Earlier, later? Who's for earlier? Who's for later? Okay, so actually it was recorded in 1967, which is very amazing, because as I will show later, this is very similar to Skype for me, and the idea and the technology were there back in the 1960s, 70s. However, this was done using analog technology. So they used video mixers for doing that, but it's still amazing to see. And so this is called the mother of all demos. It's Douglas Engelbart. In this demo, they also presented the mouse. And if you want to see the real devices of this, you can go to Santa Clara, I guess is where the Computer History Museum is. There they have the original stuff standing. Okay, 67 they had that. Let's continue to the next guy. Alan Kay, by the way.
By trying different sizes of things, we realized it should be really thin, should be light, it would have a stylus for drawing on it, wireless network, flat screen display, keyboard, and all that stuff. So this is kind of the thing I used to hold up back then of what computers should be like.
Okay, so also amazing. So this is another piece of computer hardware. Any guesses when this was recorded? What did you say, 75? Okay, let's have a look. So it was at 72, almost, very good. So you're sensible now already? Okay, so Alan Kay is the guy who did lots of human-machine interface stuff. He did also the logo programming language, so he's also a very important person. Also like Douglas Engelbart. All computer scientists should know that the two exist and what they roughly do. Okay, now we come to the third.
Here's what I've drawn for the animated section. It's an MPAD, a base station, and a workstation. See anything you want to add to that?
Well, we could add a second pad to show that there isn't a one-to-one correspondence between pads and base stations. I know. We could put it on a tether.
Yeah, I think that might work.
What are you guys working on?
It's the animation section of the MPAD video. Can you think of anything we might need to add to what we've got here?
Well, perhaps we can add a base station here and a radio. To show that the MPAD can roam between base stations. Definitely. Seamless, uninterrupted communication is an important issue.
How's it going?
Oh, hi, Ron. Well, we've added an MPAD tethered to the first base station, and we've added a second base station to animate roving. You see anything you might want to add?
Well, that looks pretty good, actually. But I know Bob had a few ideas. He's still busy hacking away for the demo, but we should be able to reach him. Bob, this is Ron. Are you around?
Hi, Ron. What's up?
Hey, we're working on the MPAD animation right now. It's all up on WB. Is there anything else you wanted to add to it?
Let me see. Let me take a look. How about adding a second pad out here, maybe at a remote location, and it could show off the audio features of the pad.
Okay, nice.
So the amazing thing about this demo is that this is the real first time where they have all this technology implemented. And so they have wireless communication and so on, and this was actually not so much later. It was in 1980 in this video. And this is at Xerox, the US company that did the copy machines and managed to invent mice, Ethernet, and so on, but not to commercialize any of it. So if you read the book about Steve Jobs and Bill Gates and Xerox, then you can read how they did not manage to commercialize the inventions, and then Apple and Microsoft did. And for wireless, interestingly, they used infrared back then, and today you might know that with the LED lights, there's also something where they try to, they did not try, I mean, they did it, communicate over the frequency of the LEDs, so it's interesting because it all comes back again. Okay, so now when we continue with the timeline, we see that in 2003 we had Skype, so it's very similar to what we had here from the idea at least. Then in 2008 we had the iPhone here, which is similar to what LK is doing there. And in 2010 we had the iPad as a bigger device. And so today, what do we have today? Well, I brought also two videos for that. So what we have today is first of all this one here. Here we see autonomous driving, and what we will see now is how this car, there will be a car coming from the right, and the autopilot is automatically preventing an accident here. And so, now the car will be coming. Okay, so the autopilot was noticing that and was going over. This partly also uses artificial intelligence technology, so this is very nice that we are able to do such things today. And this is the second example.
What these things do and how they work. So we're going to go ahead and start from the first box here. And just go open up. First thing we're going to do is we're going to put it back on.
Okay, and so why did I show this video? Because it's not only big companies that are able to do things, but when you're at home and you have money and time, then you can build your own system. So there, the Arduino or the Raspberry Pi are products that were not available 15 years ago, and today you have 3D printing and so on. So we are living in a very good time for doing this magic in the environment, because we can create all the things. If we miss some tools, we can just print them and connect them. We only need some basic technical skills to do so. And this is a really great thing. And if you would have been sitting here 15 years ago, then people would have paid you very high amounts of money for creating something that you can do today as a toy project on the weekend, because you just didn't have the tools from the hardware side and also not from the software side. Okay, good. So this brings us back to the overview. So there are also some references if you're interested to continue reading in that direction. And yeah, so this was the introduction to why does it matter, IoT meets AI, where are we at the moment, what is the history, where we come from. Okay, and that brings me to handing over to Chris. So, do you know this presenter? Because it's irritating, because it's just a guru, but you see the point there, and it's also on the recording. So I would recommend use that. If not, I also have another presenter.
Okay, so good morning, everybody. For the next, let's say, 15-20 minutes, I would like to give you some insight into IoT needs AI from an industrial perspective. Certainly not covering every detail and every aspect of this topic, but more setting the stage for the presentations to come and also for the challenges to see in the program. So my name is Chris Winkler, and I was already introduced by Fabian, so thank you for that. And that's why I can directly dive into the topic. So when I think about industrial IoT, our vision of the industrial IoT finally is the collaborative industrial IoT. That means that we will see a world of smart things that collaborate in a self-organized way to accomplish tasks, complex tasks, in a goal-oriented manner. So you are not tasking the things as we did in industrial automation for the past 20 years, where much of the automation was pre-programmed and pre-arranged, but the things are able to detect what they should do and who could help them, with whom they can collaborate with these things. And to achieve this, of course, we have a mission. That means we need to make the things smart. So from an industrial perspective, how does the evolution of the industrial IoT look like? So as you know, the whole thing started, like shown here on the left side, with more this cloud-centric idea of IoT, which is also, I think, quite predominant in consumer IoT settings, where machines and also sensors send some data to the cloud, and then you find some applications on the cloud that do magic things with this data. Easy things like dashboarding, but also predictive maintenance and all those nice applications. But industries very fastly realized that this cloud-centric, this cloud-only model doesn't really work for all the industrial requirements. And that's why we now are in a phase where we push more and more of the processing capabilities back again down closer to the field, either to edge devices, dedicated compute resources that can host edge applications, or even to the devices themselves, making the devices smart. And why is this so? Well, one reason is because of the sheer amount of data that you need to process for industrial IoT applications. Think about vibration data. Think about imaging data that would be that you would need to transport the cloud to the cloud for analysis. So that this is on the one side a bandwidth problem, but also a cost issue. The next argument is that is reliability. So if a cloud connectivity is part of your process, and your process somehow needs to work reliably, then it is probably a good idea to have this part of the processing locally closer to the field, instead of having this unreliable cloud connectivity within your control loop. The same is true for real time. So if you need to act in real time on the data that you want to process, then having some cloud sitting somewhere, maybe even in a different country, might be a bad idea. And last but not least, an argument that we often hear is data privacy or intellectual property protection. So many companies are reluctant to send all of their data via public networks to public cloud, even if you can convince them that everything is somehow encrypted. But nevertheless, as soon as you do processing in the cloud, the encryption is broken. And that's why they are not so willing to send all their data to the cloud. Now, this is the phase that we are currently in, to introduce more and more capabilities closer to the field, on the field devices, on the edge devices. And this can be data pre-processing, but also can be machine learning or trained models and all that stuff. And so to say, a logical next step of this evolution is to come to this collaborative IoT, where the smart machines start to interact with each other and start to perform tasks along given goals autonomously. Autonomous cars, as we've seen them on video, is certainly one example, but we will see increasingly autonomous machines also in industries. But if we now talk about smart things, what is the smart part of the smart things? And we tend to use these three terms here to describe what a smart thing is for us. it's the first thing a smart thing needs to do is to somehow create a self and situational awareness. So get an idea about the own situation, the own status, but also an idea about the environment, what is in there, which other participants are in this environment, what can they do for me. So this is creating a self and situational awareness. The second step is certainly to be able to integrate into this environment and to adapt to this environment. And last but not least, and that's what the ultimate goal is overall, is that the smart things then autonomously can perform tasks and collaborate in this setting. Now, what is the prerequisite for this smartness? The prerequisite, the self and situational awareness, is something that also we as humans, of course, use when we want to integrate into an environment and then start doing things in this environment. Oh, this is maybe not the latest presentation. Okay, so I start with this one here. And how humans do it is more or less depicted on this slide here. So we have, as humans, we have a lot of sensors. Our eyes, our nose, with touch sensors, vibration sensors, whatever you think. We do, or our brain does a lot of pre-processing of the sensor values, and nevertheless, to really make some meaning out of this raw sensor data, we would also need some background information, so some experience, some knowledge. Like on this example here, you may somehow be able, or your sensing may be able to generate this picture of obviously a church or cathedral, but only combined with background knowledge, with background information, you are now able, or you can know how to behave in this environment. For example, if this is an environment where you typically should behave a little bit silently, or where special rituals are typical. So it is the combination between sensing, data processing, using different types of processing. In the case of humans, of course, some pre-programmed, some learning, and then knowledge and experience. And the same is, of course, also true for technical perception. So making sense out of your environment involves sensing on the one side, pre-processing the raw sensor data to come to, let's say, meaningful information from the sensor data, like, for example, doing the Fourier transformation to calculate frequencies. But to really make sense out of the data, also here the combination with background knowledge is really worthwhile. We call this often digital twin of the system under observation. And the digital twin could contain numerical models, physical models, also learned models, trained models, but also information about the system environment. For example, if you measure a vibration value on the left side and you calculate frequencies of this vibration, it might be interesting that you know that this is a vibration, but the value of this information increases a lot if you know that this measurement is taken in a bearing, and this bearing belongs to an axis, and this axis is part of a windmill, like on this picture here, and the windmill has 3 blades. So a typical vibration scenario for a windmill with 3 blades would look like this and this. And if you observe an abnormal behavior or normal pattern of your vibration, then you can also take the wind measurements into consideration and deduce that obviously there's a very special wind situation, and that's what causes the anomalies in the vibration and not a break in the bearing. So, like with the human perception, sensing and perception, the combination of sensing, processing the sensor data, and combining it with background knowledge, with models, with simulations, using AI technologies or other maybe algorithmic technologies, brings us to this point of self and situational awareness. Now, and to give 2 concrete examples where we do this really in products, this is more or less a relatively straightforward example. Nevertheless, I personally find this quite interesting. This is the smart motor. So it's an electrical motor where you put a sensor box on the outside of the motor that can measure some values from the outside of the motor, namely temperature, vibration, magnetic field, and send this to somewhere to be processed, in this case to an edge device that processes the data. And what can you do when you combine this raw measurements with background information? In the motor example, it's the CAD data of the motor, it's the temperature model, it's magnetic field models, is that from these measurements from the outside you can calculate values that you never measured, like the speed of the motor, or using the current plus the magnetic field, you can also calculate the torque, the forces on the motor. By combining this with the temperature simulation model, all of a sudden you can then calculate the temperature on the rotator of the motor, which you never directly measured. So you get insights from the raw data by combining it with background information that was never that you would never have gotten without this background knowledge about the motor. So in this example, again, the combination between measurement, background information, and using some AI technology to really calculate the values is the key for this self and situational awareness. Another example fiddles around with those here. Those are these overhead lines, so high voltage overhead lines. They need to be regularly inspected for breaks, for birds' nests on the poles, and for other problems. And how we do this is by using drones. So drones that are equipped with a lot of sensors, like cameras, like infrared sensors, like ultraviolet sensors to detect sparks, like acoustic sensors, and they fly along those overhead lines. And again, in this example, the combination of those measurement values with background information on the context, so on how the insulators look like, what are typical problems, geolocation information, plus trained models, for example, for the image analysis, so to detect cracks on the porcelain insulators. This is done via a trained model on the image stream. And this allows you then to more or less autonomously come up with a failure pattern for, or okay and not okay and failure pattern for this overhead line, like there is a bird's nest, or like there is vegetation growing into the path and all that stuff. What we want to do as a next step is, since currently the drones are more or less flying along the overhead line, and trying to make up so to say, their mind about the situation, the next step would be that when they detect something unusual, that then the drones autonomously start to inspect this in more detail and decide which kind of pictures they should take, from which angle, which measurement they should use for the situation that they have detected. This is certainly a next step that involves more autonomy as these drones have today, because today they more or less follow the lines. And this brings me to the collaborative IoT part. As mentioned, we think that we will see more autonomy in the things, and then we will certainly see more collaboration. And why should we do this? Well, in the more hierarchical IoT networks as we have today, it's more or less, even if we have edge computing, it's more or less still a more hierarchical setting where the field devices often more or less communicate only up and down, but to cover more dynamic scenarios where the environment changes, where the capability changes, where more or less the communication partners appear and disappear, and the question whether you want to interact with somebody or something is dynamic, then this type of more or less flat structures where, like in a peer-to-peer network, things and humans and clouds and edge app devices can directly interact to perform a task, is certainly the more flexible architecture. And this brings me to one example that we do currently. And this is also, by the way, an example that you'll see in one of the challenges, not this concretely, but AGVs. This is automated guided vehicles that perform transport tasks. And in this case, it's different types of vehicles, and they negotiate with the infrastructure who is taking the next transport task. Like in this example here, there is obviously a machine that needs something to be carried to the next machine, and it calls this cloud of collaborating AGVs who can do the job. And the flexibility here in the setting comes with the fact that you can add and remove additional AGVs or take out AGVs, and the system will still work without any reconfiguration analysis. So, then since you're now in an interactive workshop, I wanted to somehow link you with two open source activities that I think are quite interesting in this area of collaborative IoT. One is called COTI. It's a collaborative IoT middleware that can be used to support such scenarios like the AGV scenario that I've shown. And the second one is a standard that has recently been released by the W3C. As you know, this is the entity responsible for the web, so they created HTML and all that stuff. And this standard is called Web of Things, and it's more or less a semantic interoperability standard. And maybe today in the lesson about semantic IoT interoperability, you will maybe also hear something about that one. And there's also an open source implementation for that one. Yeah. I think we will share the slides afterwards anyway, so you can find the links in the workshop material. Okay, so this is what I wanted to bring to the table for setting the stage for the lectures that we have today and tomorrow in the area of industrial IoT and AI. So you see related talks here on the agenda, and also two of the related challenges that have to do with edge computing, with AI on the edge, and that have to do with these AGV scenarios. So, thank you.
Okay, very good. Thank you very much, Chris. Coming from the industry perspective, I want to use some time now on the research perspective on things that we are working on. So we're doing IoT research since 2008. So we're also for quite some time in the business. And I just want to summarize a little bit, like, okay, what are the challenges? Chris already mentioned the key challenge, namely semantics. But first of all, jumping quickly back to what I said at the beginning. So probably you know about virtual reality. So this is again about terms. So virtual reality is that you put yourself into the computer. So you take something like the Oculus Rift, someone gets that on, and then you're part of the computer. Then the next thing that is there is augmented reality. Augmented reality is you have smart things, or even glasses that augment your reality. That means you still see the reality. It's also used a lot in production already today. When you have glasses on that tell you, for instance, which parts to take from which shelf, or where the error is in the physical hardware that you should fix. And then you have pervasive computing, and the interesting thing is that pervasive computing, you don't need any devices. So it's just happening around you. Why is this interesting? Washington, by the way. Because when you look at this development, so we're coming from the left to going to the right, things are also happening somewhat in parallel. The technology awareness diminishes. So when you have a physical space that is enriched with smartness, you're not aware of that. And this brings implications. For instance, regarding privacy, regarding security. If suddenly a robot arm comes and smashes you down, you should be aware of that this can happen, for instance. At the same time, the technology immersiveness increases. So, for example, with the robot arm, or with if I would walk here and the Twitter wall would follow me, or the phone call follows me, this is very immersive because it's happening everywhere around me and I'm directly part of it. So my physical space is getting changed by the software. The pervasive computing space ideally looks in a way that we do not see that is technology enriched. Okay. So what are the challenges? So the biggest challenge for implementing IoT use cases in the true sense of doing magic is that you have silos. So you have systems that are not interoperable. So they cannot talk to each other. So you cannot easily program the industrial robots to manufacture a car when your alarm clock at home is ringing, for instance, because there are just no direct interfaces for them. So So this is a challenge. It has to do with vendors, with functions. It's also a spatial challenge, so you have to get connectivity. And the LoRa challenge will focus on that, where we have wide area connectivity. It's also a technical challenge because you will never have the single protocol that is fitting everything. Just think about, you have a Windows sensor that is battery powered, and at the same time you have your laptop, for instance. So both do have totally different requirements on the communication technology, communication protocol, and so on. And therefore heterogeneity is not something that is an error, which we have to overcome, but it's more like, okay, this is a part of the technology. It's because the technology has to fit different purposes there. Something that is done then to bridge these silos is middleware. So middleware, in a nutshell, is taking a distributed heterogeneous system and providing a unified system view. So for you as a programmer, that you can note this and don't have to worry about the computer went totally off here. So he's not happy about what I'm saying. System view on the heterogeneous distributed entities. And so what happened over the past years is currently happening in the home space is that there you have then some hub devices that are connecting different entities. But the drawback is that when you go to the ecosystem of this vendor here, for instance, that they only allow you to do things that they want you to do. So you are not free to create what you want to do there. On the industrial side, it is a little better because there we have standardization. So we have some more standardized protocols like OPC UA, for instance. And so within their domain, these protocols are providing good functionality to do things. But as I told you at the beginning, the cool thing about the AI, the IoT, is that you can connect whatever you want to connect. And yeah, battery was indeed empty, sorry for that. And to do so, you have to integrate the Apple ecosystem with the Google ecosystem, the Siemens ecosystem, maybe with other vendors. And this is challenging, and middleware that wants or that can enable you to do so is not so easy to create. And then the rest of the talk, I want to focus on some important challenges. And yeah, so here we are. Let's just replug. Okay, good. Okay, perfect, good. So, yeah, heterogeneity, distributedness, so all over the world, different devices, brings complexity, and someone has to handle the complexity. So with the smartphone, it's the application developer, because if you have some Bluetooth devices that are connected, for instance, you have to implement the stack that understands the protocols that are running there. The middleware provider could do that, or the one that is providing the device, but the device doesn't know about the other complexity levels. When you want to structure such automation here, you can think about it as shown here. So the pointing device is also not working. Oh no, I was pressing wrong, sorry. So let me just start also the point thing. Okay, good. Okay, so when you think about this setting here, then, okay, I do it without. What you have is, at the bottom you have the physical environment, so the thing that you want to interact with, and on top of that you have the sensors and actuators, so these are the interfaces to your physical environment. On the other side, on top, you as human want to give some input. So you want to set, for instance, that the robot arm should go to a certain position, or that you want to produce some certain parts of a car at the moment, and therefore you need some human-machine interfaces. This is what we see on top. Then we have software, so this is called services here now, and then we have what Chris already said, namely semantics or data in the middle. So this is the normal compute process. You have input data, you process, and you have output data. And therefore you have this in the middle. And therefore what we do for the past 11 years is we work on semantic middleware. So context-oriented middleware. So context is basically, in the broader sense how I use it, all the information that is needed to fulfill the goal, the tasks that you want to do. So if you want to produce something, all sensor input that you need and all control output that you want to send to the devices that do something. Around that we have then services, and then these services have different purposes. So the ones on the bottom interface these devices that they can remotely manage, and the ones on top provide control and they provide user interfaces. And then you need to connect these services, and what we do is we have a micro middleware with microservices. That means you create small building blocks and you can connect them in order to implement complex functionality. So this is our way to tackle the complexity. And to do so we have different mechanisms. So we have a publish subscribe, and we have normal REST interface where you can get and set information, and something that is used for having direct coupling, so-called virtual nodes. And using such a middleware is very interesting and very nice, because you can use a very simple form of programming, namely you can use event condition action rules to invoke complex tasks. And this is quite nice, and the people working on Challenge 3, you will work a little bit with this middleware and see a little bit what it does. What you see here already is that I put circles, and the circles have the same color. This is of course on purpose, because what you can do is you can unfold the entire thing, and then you have the physical reality, a interaction level layer between the physicality and the cyber, so also in the broader sense cyber physical systems there, and then you have data on top of that. The classical stack looks like this. So you have at the bottom again the reality, then you have the interfaces, then you have software drivers, management software, and then on top you have the humans. And we explicitly put in this context management. This is what our middleware does, and it helps us to provide lots of support functionality, especially also security, where I'll talk about on Wednesday. When you look at it more in detail, the thing we implemented as a peer-to-peer system. So you have so-called knowledge agents on all nodes. They are managing the data and also the interaction between services in here. And you have different functionality that has to do with what Chris said before, namely the semantics. So we have something that is called Semantic Discovery here. Okay, so more details. If you want to know more, you can just approach us, one of us from my team, and Challenge 3 team will also see more of it. So now let's have a quick look at an example. So this is actually the game that we see in the back here, and we have the two sensors on the left and the right, and then we have some alarms, and we have some remote compute functionality here. And the interesting thing when you have a data-driven approach is that the first thing you have to do is that you have to model the data that you want to interact with. So this is the first step when you program. So you don't write the functions, you write a data model first. And so this is what you do here. And then the functionality of the services here is to reflect between the reality and the data, the semantic model of the reality. And this eases the programming of such an environment a lot. Okay, so you have a mapping here, and this one, the task of this microservice here is just to reflect between the virtual representation and the physical entity. Okay, then we have here our overlay connectivity at the bottom. So this is happening autonomously, so the programmer does not have to take care. And a crucial part of such an architecture is that all these components here are loosely coupled. And that means they all have to work on their own. They do not rely on the others to work. Of course, you can have processing chains where all these here work together to do something, and if a part of it is missing, then the entire process is of course not working. But the components can be used by multiple processes at the same time, which is also an advantage of this abstraction here. And therefore, if something is going down in the chain and someone else still wants to use one of the services, this is still possible in there. I said it's very easy to program that. So on the right side, you see pseudocode for the game here. You see, okay, we wait until the hand is on the boxes, then we set the alarms to on, then we wait for a random delay, or a trigger, then we trigger the boxes, then we wait until the hand was removed, then we get the times, and we set the alarms so that it shows what is happening. And I could not have written it much shorter for explaining you how the algorithm works. And the nice thing is that you can program this almost like that down when you use the VSL, the virtual state layer, so the thing that virtualizes the physical state in this virtual state layer here. And so on the left side, we want to set now the trigger here later, and first of all we want to get the lux value of the box 1, and the nice thing is we can just use a hierarchical notation here, because we just have to find out, okay, where is this address now, where's the instance of this node, and then we can directly go to it and get the data. Okay, this is what we do here. We do the same for the second box, and if both are above this threshold, then we get the time. So this is also very simple of both boxes. Okay. Okay. Sorry, I made it really short. I can show a little bit more on Thursday. And so what is interesting now, I have not this slide here in, but what is interesting, that we have a semantic decoupling. So you can search for, I want to have an input box that is the input controller for the game, somewhere connected to me, and then the system will return you all instance addresses of these nodes. And I will show you a little bit more about the data model in some slides. And the good thing is, if you know now this is the input box in our system, the entire data layout is fixed beforehand. And that means if you know one of the nodes, you can relatively access everything below. And this is quite useful. Okay, good. So now let me click through it again, because I jumped over it, or maybe I can click here. Okay, so Chris mentioned it. Semantics, very important. And so when we talk about semantics, you might have heard about ontologies. So this comes from the philosophy area. So an ontology is about words describing something. And for instance, a real-world example is you would say, okay, a chair has 4 legs. Okay, it's even wrong for these things here, but a chair would have 4 legs and everybody would understand, okay, this is a chair. Okay. So this is an ontology. So you describe something with a model so that everybody can talk to each other. So language also uses lots of ontology concepts because otherwise we could not speak to each other. Then there's something that is called upper ontology, and so this is the common ground for all people. So when you think about, again, language, if you have people who are totally into cars, for instance, they might tell you 1 million parameters of a car. And if you are me, then you have no clue about it. Then you would say like, well, okay, it's red and it has 4 wheels. And so we have a common denominator, some common ground, which is the basics that we need. And this is helpful for interoperability between different people now, but also between different services that want to control something. And the upper ontology is this common ground. When we come now to computer programs, we have virtual objects. So this is this virtual representation of the data. Then we have models that define how, for instance, the game controller layout is of this data. And we have a meta model. And so the meta model is, for instance, XML. This one here is then defining, okay, which nodes does it have? And the virtual object is then the instance. Take home from this slide is just, okay, we have a virtual representation and it follows concepts that we know back from the past, and it's very powerful to do so. Okay, second aspect I want to highlight in this talk is this one here. So once you have this microservice architecture, you need lots of services. And therefore, you also need an app management. And my vision is that we have something similar to the smartphones, also for factories and for private spaces, and it's also happening. And the idea is we have developers, they develop something, they put it to one or multiple stores, and from there you can deploy it to the different sites. And there, again, to manage the complexity, you need autonomy. So you need autonomous management. So why do you need it? Because when you install a software, or why is it challenging? When you install a software on your smartphone and it doesn't work, well, you have a screen. You can interact with it, you can stop it, you can remove it. But when you have a wall plug, for instance, and the wall plug does not work anymore, you will probably not remove the wall plug and fix your installation there. And it's the same for when you have industrial automation devices. They are normally not accessible in an easy way, and they don't have a human-machine interface. And therefore, you have to take a lot of care when you do updates, for instance, have rollback mechanisms, and so on. Okay, and so this is what we see here. Could give you more details, but I want to leave it for that right now and come to the end of my part, namely, what can we do with this magic? So I found a very nice application when I finished the slides yesterday and just want to share it with you. So there are these nice guys, and they created an interesting robot that has an interesting configuration. What is interesting is also the size and power of this device, so this can easily smash you. And they mounted a very interesting thing at the front. Let's see what happens. This is actually a chainsaw. And so this is chainsawing right now. And so let's see. Okay, so it stopped, and so I went forward again, and so now we see what they created. This robot created some 2 chairs and also a table, and very nice application. And also very nice because we can just do it today. I mean, you will not buy this expensive robot there, but there are also smaller ones, and your creativity doesn't have a limit. So they thought this is a nice application. But why did I put this? Well, because an important aspect that I also want to talk about more on Thursday is this one here, on Wednesday, is this one here, namely security. Part of it also safety. Because if someone, for another reason than fun, or also for the fun reason, mounts a chainsaw that is remotely controllable on such a robot arm and it's standing in front of you, then you definitely do not want that the update cycle is moving it to you, or that someone is hacking into it, or whatever. And therefore, security very important. More about that on Wednesday morning. And this brings me also to the end. Thank you, and Chris and I are open to your questions. So who has a question? Maybe Chris, you also come up. Yeah, wait, we give you the microphone. Maybe one of my people from the back could do that.
Hello, everybody. I have a question for Chris, and you spoke about the change between hierarchical IoT and decentralized IoT. And I want you to ask, for you, what is the main driver to go through there, to go to decentralized?
The centralized or now the decentralized?
Decentralized.
The decentralized, right. You know that this discussion about centralized versus decentralized is like a pendulum, and you will see it repeatedly. And so to say, we also had this in the introduction about computing, from mainframes to personal computers, then back to cloud, which is rather a centralized model. Now we are talking about edge. Some of the arguments for the edge stuff, so the, again, more decentralized, I've already given in my talk. Oh, sorry. Hello? Yeah. And regarding the decentralized, let's say, collaborative, of course, you could, for example, this AGB scenario that I showed you, you could also have a central controller that knows everything and then manages this fleet. Yeah? But we think that in particular in scenarios where you have a high dynamics in environment, in tasks, changing situations, changing communication partners or partners that need to interact to do something, there this notion of more smart things that can really directly interact seems to us more helpful and seems in this sense a little bit easier to implement and cater for those types of scenarios. But still, I mean, you could also, of course, do this in a central way. Well, that's what we do today, bring the smartness to the edge, to the devices. But of course, for many scenarios, you could also have a central controller, putting aside the requirements that or the conditions that I mentioned in my talk, like real time, like reliability and all that stuff, or security. Yeah. But currently we think that due to the fact that it is now possible to really have, for example, also AI close to the field because of those nice AI accelerators that you can now really put down to the field devices, to the edges, it is simply, it seems to us, architectural-wise, simply wiser to do it like that.
Hello. So the two typical reasons for it are the latency and the resilience, of course, also. Because both you can have, but you buy it as more complexity for the management. Okay, further questions? Here, in front, Stefan.
Hello, my question still relates to that. So you have a centralized system and a completely decentralized system. So wouldn't you say a hierarchical system is like having the best of both worlds? Why would you want a completely decentralized system?
You mean completely decentralized?
Yes.
Well, to be honest, in industries we'll probably never have a really completely decentralized system, simply because of the reason that, for example, for managing the devices, even the simple thing of security updating and all that stuff, updating the apps, updating maybe the models, the AI models on the devices, for that it's in industries, I think you will always have this combination of some central functions like device management functions sitting in the cloud that then can manage the substrate below. But I think what the biggest change is that in the strict hierarchical approach, the feed devices would more or less talk only to the level above. Yeah, but now in the decentralized, they start interacting, so they start talking to each other. Yeah, like the AGBs that now start negotiating who takes the job, without having to go to the central entity. So in practice, in industries, we will have a mix. So it will certainly not be a pure decentralized without any let's say, central component.
More questions? Stefan?
Sorry, I don't want to centralize, but the cool thing would be to know which components should be, let's say, in the orchestrator or in the centralized part, and which in the decentralized part. So
yeah, sure.
That was the question. And
okay, and I mean,
I think we will know in the in the summer school.
After the summer school, maybe we know more, but certainly functions that you need to manage the overall system well lend themselves pretty much to being centralized, at least in those settings that we have in industries. Yeah, but regarding functionality, I mean, I think it's like the border conditions, like mentioned real time and all that stuff, that gives you some hints where it would be applicable, or compute power. I mean, it may be worthwhile to have an AI model executed on the edge, nevertheless learn over fleets in the cloud. So, as I said, probably we'll see a mix of both.
Okay, yeah, then. First of all, thank you again, Chris, for the talk. And just unfreeze. So, as you see here, the next part is you can stand up and have a coffee. So we do the coffee break, and we'll continue at 11. So this means you have now about 16 minutes for the coffee break. So we try to have a little faster coffee break to catch up a little bit with the late stream. Okay, see you in about 15 minutes.